Okay, so we'll have a second talk by Professor Sungwon Kim on the another representations. Yeah, so we can start.
Okay. Okay. So now, so today what is the analysis of representation and what is the motivation for the analysis of representation and so on, and history and the examples and so on. So let me first read the calligraph. So because the analysis of representation is defined for the word hyperbolic group action on some metric space, so we need to define first the calligraph and its the ideal boundary. So let gamma be the group and choose some symmetric generating set S of gamma. So then you can associate some graph, so namely the calligraph. So as follows. So first, take a vertex set as the set of the elements of gamma, and take an edge. So G1 and G2. If and only if G2 is written as a G1S for some generator, the S in the chosen generating set S. So after that, now that we have a graph, right? So and we want to this graph into some metric space. So set the ranks of each edge in the graph to be 1, and define the distance between the G1 and G2 to be shortest the ranks of the path from the G1 to G2. So we call this metric the word metric, and then the calligraph becomes the metric space. So given the group of gamma, then we have a graph, right? And actually the metric space. So then we want to define the notion of the group of hyperbolic space and the word hyperbolic group. To define this, we just deal with the generic geodesic metric space. So let X be the geodesic metric space, then if every geodesic triangle is delta stream, then we said that the X is a delta hyperbolic space. So I will give what is the average geodesic triangle is a delta stream. So anyway, if it is delta hyperbolic space for some non-negative constant delta, then we say a metric space is a hyperbolic space. Sometimes word hyperbolic space, sometimes the group hyperbolic space. So then what is the delta stream, the geodesic triangle? So a triangle, geodesic triangle with the vertices x, y, g is delta stream. If the geodesic segment of x and y is contained in the delta neighborhood of the other side segment. So this condition gives us some geometric view of delta stream, the geodesic triangle. So geometrically it looks like this. Okay. So x, y, g, and the x, y segment is so this is delta neighborhood of the segment, geodesic segment x and g, and this is a delta segment, delta neighborhood of the segment y and g. So like this. Okay. So this this condition gives us some geometric the meaning like a slim. So that is why we call the data slim. So the geodesic triangle looks like a very slim. Okay. So here is a very extreme example. The red F2 is via the free group of rank 2 with the symmetric generators, the generating set A, B, A inverse, B inverse. So then it's a carry graph looks like this. So you can easily check what is the carry graph is. So then this carry graph is a zero hyperbolic space. So because this comes from the fact that there is a unique geodesic from one point to other point. Okay, so if given a two distinct point, there is only one geodesic connect them. So, for example, think of the geodesic triangle where this is B, A, so A inverse. Okay, so then this is a geodesic segment from A inverse to B, and this is also the geodesic segment from A to B, and this is a geodesic segment from A inverse to A. So then, so you can easily see that the geodesic triangle is zero slim. Okay, so the carry graph, the associated to rank 2 free group is a zero hyperbolic space. And you can see that when defining the word metric, the chosen symmetric generating set is inverted. So if you choose the different symmetric generating set, what happens? So in the carry graph. So known fact is that the carry graphs associated with the different generating sets are the Cauchy isometric. So what is a Cauchy isometric? So Cauchy isometric is some idea of so that respects some large scale geometry. Ignore the small scale details. So definition is the map F between the metric space from X to Y is called the LA Cauchy isometric embedding. So if it satisfies this, okay. So F does not deform too much with respect to two metrics, and the Cauchy isometric embedding is called the Cauchy isometry if so there is some C tens in in Y, okay, and also the array Cauchy geodesic in X is array Cauchy geodesic embedding of the interval in the real numbers into some metric X. So anyway, this is a Cauchy isometric things. So as I told you, the different carry graphs associated with the different generating set are Cauchy isometric. So there some information that are the invariant under the Cauchy isometry. So like the ideal boundary of the carry graphs. So let's see now to look at look at the boundary at infinity of the hyperbolic space. So the ideal boundary of the carry graph is defined, and so as usual, right? The equivalence class of the geodesic rays under some equivalence relation, and it is invariant under Cauchy isometry. So because of some Morse lemma as well. So, but anyway, this ideal boundary does not depend on the choice of the generating set. So we denote by some boundary of the group gamma. So we denote by like this. So example, so first, the ideal boundary of rank 2 free group is homeomorphic to the contour set. So you can easily see this, and also the ideal boundary of the closed surface group. So closed surface group is also the hyperbolic group, and its ideal boundary is homeomorphic to circle. So like this. Okay, so now we will look at the Schottky groups in PSL2C first. So because the motivation for convex co-compact groups or the analysis of representation, comes from the Schottky groups. Okay. So let's consider some elements A and B. So this is in the PSL2C. And also you can see that the PSL2C acts on the CP1. So CP1 is homeomorphic to S2. And it can be regarded as an ideal boundary of the three-dimensional hyperbolic space. So anyway, the PSL2C acts on the CP1. Even if we don't know the SL2C is the isometric group of the hyperbolic 3 space. So, and then suppose that there is some disjoint domain, the 4 disjoint domain, the dA, dA inverse, dB, dB inverse. So such that it satisfies like these 2 things. So they mean, for example, so outside of the dA inverse, so this one, okay. So this is a shrink to the dA, domain dA, okay, by the action of A, okay. So the domains, also the similar, the property. So then this is the Schottky group, and we know that the group generated by the A and B is a free group of rank 2, and it preserves some complex offset, so lambda of CP1, and that the lambda is a homeomorphic to a contour set, so which is exactly the ideal boundary of the rank 2 free. So this is a very classical the Schottky groups. So, but what is geometry key, the property behind the Schottky groups? So here, you can think of the geodesic rays passing through the identity in the Carry graph of rank 2 free group. So then there is the one-to-one correspondence. I mean, the nested sequence of open domains whose diameters tends to 0, the exponentially. Okay. So here is an example. If you consider some geodesic in the Carry graph of rank 2 free group, so this is just AB, 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 AB. So maybe here you can see what is the geodesic. So here, so A, B, A, B, A, B, A, B. So this geodesic, okay? So this is a geodesic in the Carry graph of rank 2 free group. So then you can associate to a nested sequence of the open domains like this. So first, so D1 is dA. So what is this here? This is dA, first this domain. And second, the dAB, we define dAB by the A, dA, dB. So I mean the image of the dB, domain dB by the action of A. Okay. So then you can see that this is inside, this is subset of dA. So because this is contained in CP1 minus dA minus dA inverse, and the dA, so this is also contain a dA, right? So for this region, we know the inclusion relation. And similarly, you can do the continuously, the D3 and D4. So in the pictures, the nested sequence of open domain like this. Okay. So anyway, if you have the geodesic ray through the identity, then you can find the nested sequence of open domains, whose diameters tends to 0 exponentially. So then that means that their intersection gives a point in CP1. So this point is in the lambda. Okay. So there is the how the Schottky domain works in the CP1. So there exists the equivalent continuous injective map from the ideal boundary of the F2 into the CP1. Okay. So because actually the geodesic ray through the identity in the paragraph, so this gives us some point. Actually, this is a point. So in boundary, ideal boundary of F2, because as I said, there is only one geodesic ray from the identity to a point here. So there is a one-to-one correspondence between the set of the geodesic rays passing through E and the ideal boundary of the F2. So that is why we have the equivalence this map. Okay. So in other words, we can say that the ideal boundary of F2 is embedded in CP4. So here, then you can have some contracting the property of the Schottky groups. So this is the important key property of the Schottky groups. So this is we just have a look at the action on the CP1, right? But if you think of CP1 as an ideal boundary of the hyperbolic 3 space, then you may ask the question of what happens inside the hyperbolic 3 space. So then it turns out that actually inside what happens, the paragraph actually is embedded in quasi-isometrically. So more precisely, if the paragraph is embedded a map like an OB map, so gamma is mapped to the gamma x for the fixed point, the x, then this map is quasi-isometric embedded. Okay. So this is what happens inside the pre-hyperbolic space for the Schottky groups. Okay, so now how to generalize the Schottky groups. What is a key properties of Schottky groups? Because the Schottky groups are stable. That means that if you have the Schottky group, then you can also perturb a little the generator. Then every small perturbation, such a perturbation are still the Schottky groups. Okay, so people want to know that why this is stable. So there's many characterization of the Schottky group, and so on. Anyway, we want to generalize the notion of the Schottky group to more general groups. So first, the rank 2 free group is extended to the hyperbolic groups. So gamma. And Schottky domain. So how to generalize the Schottky domains to what? So for in general, we cannot find the Schottky domain, the Schottky groups for the hyperbolic group action on at the infinity. So anyway, the first the paper gives the boundary map, the notion of boundary map. So there exists the continuous injective and the gamma equivalent map from the ideal boundary of the gamma, I mean the hyperbolic group gamma, into the boundary of the hyperbolic space, the boundary of the hyperbolic 3 space. So actually, this is enough to extend the notion of a Schottky group to the more general. So actually, because due to the negativeness of sectional curvature of hyperbolic 3 space, so expanding the contracting property like a Schottky group follows from just the existence of boundary map. So, however, in higher rank, it does not hold. So we need a more something. Okay. So anyway, in hyperbolic 3 space, I mean, in rank 1 case, so the existence of boundary map is enough to defining the generalize the notion of the Schottky group. Second, so as I told you, the action, I mean, look at the action on the inside the hyperbolic 3 space. So orbit map from the calligraph into the hyperbolic 3 space is the Cauchy isometry embedding. So this is also the stable thing, and it is enough to characterize the Schottky groups. And second, this is also special. I mean, the particular property which holds in higher rank, rank 1 case. So there is the convex subset of hyperbolic 3 space on which gamma acts the co-compactly. Okay, so actually the 2-1 and 2-2 are the equivalent condition. And the third, the expansion, the hyperbolic actions given by the Sullivan. So Sullivan gives us similar pictures like the Schottky domains. So he defined some expansion hyperbolic actions. So let lambda be the gamma invariant, the compact subset of the ideal boundary of a hyperbolic space. So there are symmetric general set S and finite open covering U over lambda indexed by S, such that each pair satisfies the expansion, the hyperbolic actions. So it's a kind of generalization of the Schottky domains. So I do not want to give details about these actions, but this is also one of the equivalent condition for the convex co-compactness. So, but anyway, in this setting, you have the similar picture like the Schottky groups, right? You have domains and some invariant the subset, namely some limit set. Then the similar thing happens. If you have some geodesic ray in the calligraph, then you can associate some nested sequence of the open domains by using these open covers and generating set. And so it turns out that it shrink exponentially to a point. Okay, so the similar thing happens as in the Schottky group. Okay, so anyway, in hyperbolic 3 space, so these all the conditions are all the equivalent. Actually, in higher rank 1 symmetric space. Okay, so we call a group with these properties the convex co-compact group. So why the convex co-compact group is important in the theory of the hyperbolic 3 space? So here is the theorem. The set of the convex co-compact groups in the character variety of gamma in rank 1. Actually, the rank 1 simple Lie group is open. Okay, so this is open. It has the property of convex co-compact group are stable. Okay, I mean the 1, 2-1, 2-2, and 3 properties are stable in the character variety. Okay, and also the in hyperbolic 2 space, the convex co-compact groups of cross-surface group in PSL2R is just a component in the character variety, and it is homomorphic to the bore with a certain dimension, depending on the characteristic or the characteristic of surface. So this component is called the Teichmann space of the surface. Okay? And also in the character variety of the PSL2C for the cross-surface group is the space of the convex co-compact the groups is open and dense in the character variety, and also it is homomorphic to the bore. So it has been the very important role in developing the hyperbolic 3 manifold theory. Okay, so now the question is how to extend the complex co-compactness to higher rank. So people want to extend this notion to the higher rank for many years. So first trial is just you just apply this condition. So this 4 condition to the higher rank, right? But it fails. So first for Zariski dance, the subgroup gamma of G, then there are no the continuous injective and gamma equivalent map from the ideal boundary of gamma to the ideal boundary of X. So in X is a higher rank symmetric space. So because this comes from the work of the Benoit. So Benoit studied the limit set of the discrete group in higher ranks symmetric space. So he verified some structure on the limit set of discrete group. So from this, we can conclude that there are no the continuous injective to gamma equivalent map. So the first condition fails. And the second, so 2-1, the Koji geodesics are the stable in rank 1 by the Morse lemma, but in higher rank, it does not hold anymore. And 2-2, the existence of convex domain on which the discrete group acts on co-compactly. But the Klein and Ree proved that if X is the symmetric space of non-compact type of higher rank, and gamma is a Zariski dance subgroup, then X has no proper closed gamma invariant convex subset. So that means that the convex co-compact groups, the convex co-compact groups are co-compact lattice in the higher rank. So there are not U1, right? So it is not the interesting definition. And second, the G action on the ideal boundary of X cannot produce any subgroup with some expansion and hypervelocity action given by the solvent. So the all, you cannot apply the all this condition to higher rank. So it fails, to prove the stability, and so on. And this gives us some new discrete groups and in higher rank. So what is the problem here? So let's back to the Schottky groups. So then let's try to construct the Schottky group in higher rank. Okay, first. So then in the ideal boundary of X, we cannot construct the Schottky group. So in higher rank. So here is the region. So for example, right, the gamma is a 3x3 matrix with diagonal 2, 1, 1/2. So this is a kind of the hyperbolic elements isometry. So then the gamma acts on the maximal flat by a translation. So here is a picture. Okay. So then the gamma acts. So gamma acts on the boundary of the maximal flat F by the identity. So that means that gamma fix all points of the ideal boundary of F. Okay. So that makes we cannot never define the Schottky domain. Some contracting. We have to construct the Schottky domain. We need to find some expanding domain and contracted domain and so on. But it fixes some circle, so we cannot find the expanding, the contracting domain. So here we can know that what is a problem here. So boundary of X is not good to construct some good groups. Like Schottky groups. Okay, so then what about the change of the domain? The ideal boundary. So key idea to extend the complex co-compactness to higher rank is to look at the action on the partial boundary. So we define the boundary. So there are many boundaries depending on the town mode, right? So let's look at this boundary. So then it is possible to construct the Schottky groups for the G action on the partial, the flag boundary, this one. So because we can see that some elements of G have a similar dynamics on the partial flag boundary, similar to the hyperbolic elements of PSL2C. So here is the example. So let's take a G SLNR, and X is a symmetric space. And town mode, just take the Y chamber, okay, sigma mode. Then we have to look at the first number boundary of the X. So take a gamma is a diagonal matrix with a distinct real eigenvalues with in decreasing order. So then there are the attracting flag and the repelling flag. So gamma plus and gamma minus. So this is a flag. Okay. So this is the repelling the flag. So then we can prove that. So here is a C gamma minus. What is C gamma minus? The C sigma for some pi chamber at infinity, the sigma, we can define a C sigma. So this is the set of all the pi chamber at infinity. That is opposite to the sigma. Okay, so then this set is open and dense in the partial flag the boundary. So actually, so this is a big set, okay? So open, because it is open and dense. Anyway, so this open and dense. Okay, so I think so there are typo. So gamma n, okay. So gamma n action, so maps to, I mean, the converts. Okay, yeah, the gamma n, the shrink the c gamma minus to the gamma plus, okay, as n goes to the infinity, and the conversely the minus, okay. So gamma n, the minus n, the shrink the c gamma plus to the gamma minus. So this is the same the situation with the Schottky the domains, right? So then it gives the similar the property. I mean there are some the expanding and the contracting property similar to the Schottky groups in the H3 hyperbolic tree space. So we can so it allows us to construct the Schottky groups in the SLNR, so acting on the first level boundary. Okay. Okay. So before the notion of the anasoc groups was defined, so 1997 the Benua the construct the Schottky groups, so acting on some pointed the flag space. So P1n minus 1 is the parabolic solver fixing this partial the flag. Okay, he exactly used the same idea, so as I described before. So he used the contracting and expanding property of some proximal, he called the proximal the element in SLNR. So by using that property, he can construct the Schottky groups. Okay, actually he gives some Schottky domains acting on this partial flag space. So anyway, after that, but the Benua does not use general expanding the contracting properties for hyperbolic groups. So he only gives us the examples of the Schottky groups in the higher rank. Okay. So in 2006, the Rabri first introduced the anasoc representation. So in the character variety of cross surface group in SLNR, actually the hitching component, right? So and then the Gisher, the Vinad, the extended the notion of anasoc representation to more general in the character variety of hyperbolic group in a semi-simple regroup. Okay. So their key idea is to use the anasoc floors in the dynamical theory. Okay. So they think about given some representation, they associate to some bundle, and then they think of the anasoc floor on that some associated bundle. Okay. So and then the 2017 the Kapovich Riband Porty gave us several the equivalent characterization in the viewpoint of geometry, the group theory. So their key idea comes from the dynamics, the action of G on the partial flag space. Okay, so here is the definition. Actually, the Rabri and the Gisharin, the Vinhard gave first the definition of anasoc representation. So I just here give a definition of coupled property. So here, the subgroup of gamma is a tau mode anisotrope. So if gamma is a group hyperbolic, and there exists the gamma equivalent continuous embedding of the ideal boundary of the gamma into the flag space of tau mode. So this is just the tau mode ideal boundary of X, sending the distinct points to opposite the simplices. So this is just the definition of convex co-convex, right? But we need more. So as I said, so here the second, we need the expanding the property. So precisely for every point T in the ideal boundary of gamma, every normalized discrete geodesic ray is noted to gamma. So that means that here is T and some geodesic gamma. So going to the T. So for this, the discrete geodesic ray R, so this is expansion. So this is expansion factor. So gamma inverse, actually in Schottky group, so every element go to shrink the domain to a point T, right? So the conversely, it's inverse expanding at the T, right? So this expansion, the property expansion factor is bounded by the above, but bounded by the below the some uniform amount, okay, like this. So actually it expands uniformly, the expanding at the T. Okay. So this is the definition of tau mode anisotrope, the group. So difference between the rank 1 case, I mean the convex compact groups is need so 2. We need a 2 condition. And also KRP gives the equivalent condition inside the symmetric space. So the orbit map, so this one is a quasi-isometric embedding. Here is they add the Morse quasi-isometric embedding. Okay, so I told you that just the quasi-isometric geodesic is not stable in higher rank. That means that if you have a quasi-geodesic in higher rank, if you perturb a little, then the quasi-isometric property breakdown. Okay, but the notion of the Morse quasi-isometric embedding given by the KRP is stable. So that means that if you have a Morse quasi-isometric, Morse quasi-isometric geodesic, then the small perturbation is still the Morse quasi-isometric, the quasi-geodesic. Okay, so here I will explain what is the Morse quasi-geodesic. So Morse quasi-geodesic is so like this. So first quasi-geodesic, it must be a quasi-geodesic, and also so this geodesic is stay away from some phi chamber by some uniform constant, and the distance between, distance from their orbit stay away from the wall. Okay, so precisely the distance of CNX and the wall, the boundary of the cone, the phi chamber goes to the infinite, and as n goes to infinite. So more specific, the quasi-isometric, the geodesic, quasi-geodesic in higher rank. Okay, and also, so this year we Kopovich and me and I and G&TFair, so prove that the gamma action, I mean the anisotropic representation, the anisotropic subgroup, the gamma action on the partial Fleck space satisfies some hyperbolic action in the sense of Sullivan. So we and this the anisotropic action satisfy the hyperbolic action in the sense of Sullivan. We proved that. So that means that the hyperbolic action, the expanding the hyperbolic action given by the Sullivan is useful in the study of anisotropic representation. And there are more the discrete groups satisfying the Sullivan's expanding the hyperbolic action. So beyond the anisotropic representation. Okay, so here the term of the Schottky groups. So this is exactly the the same thing as the Benoit did. Okay, so there are some elements of gamma which acts on the partial Fleck space, like the hyperbolic, the isometry in hyperbolic space. So it has some expanding domain and contracting domain and so on. So from that property, you can always construct the Schottky groups. So acting on the partial Fleck space. Okay. Okay, so here is a known fact. I will finish. Just let me know what known facts. The first, the convex co-compact groups are Anosov, and Hitchin representation is also the Anosov, proved by the Rabri. And the Hitchin component is called the higher Teichmann space. It is also homomorphic for the Teichmann space. And Fogg and Goncharev introduced the notion of positive representation, so which include the Hitchin representation. So in particular, in PSL3R's case, the Hitchin component consists of the convex product structure on the sigma. So is it proved the Goldman and Joey and so on. And this year, we also proved that the Kopovich and with Kopovich and G&TFair, we proved that actually we extend the notion of the expansion hyperbolic action in the sense of Sullivan to a more general, so which works for the uniform lattice, I mean co-compact lattice in the semi-simple Lie group. So let the gamma be a uniform lattice in a semi-simple Lie group G, and P is the parabolic subgroup G, then the gamma action on the partial Fleck space is mindering the hyperbolic. So it turns out that the mindering hyperbolicity is also stable in the character variety of the gamma in G. So that means that this is a step. And also the mindering hyperbolicity works in the setting of metric space, just a metric space. So there are a lot of the flexibility and so on. So it may be the interesting object to study the anisotropic representation, some more the interesting groups. So yeah. Okay, so I stop here.